Hi everyone, welcome back. This video is a continuation of our discussion on sufficient statistic, and we will focus our attention on the factorization theorem. Let's first review what we've learned so far. I started with the definition of sufficient statistics. Basically, we call a statistic Tx to be sufficient if the conditional PDF of the random variable x is independent on theta. So when this hx is not a function of theta, we call Tx as a sufficient statistics. Then I introduce a theorem. This theorem states that the ratio between the joint PDF of x and the marginal PDF of the statistic is a constant function, is constant as a function of theta. We used an example of Bernoulli trial to illustrate how to use the definition and the first theorem to show the sum of xi is indeed a sufficient statistics. So today, I'm going to introduce factorization theorem to you guys. It's another way of showing Tx is a sufficient statistic. Again, let fx denote the PDF or PMF of a sample x. We call a statistic Tx is a sufficient statistic if and only if there exists function g, t, theta, and hx such that for all sample points x and for all parameter points theta, we have the following equality. So the PDF of x is equal to g t of x given theta times h of x. In other words, we say that f of x can be factorized into g and h. Here, we specifically define g is a function of t of x. Since it's conditional on theta, and h in this case, without theta, it has to be constant to theta. We will say Tx is a sufficient statistics if and only if we can factorize f of x into a function of theta and a function that's constant to theta. Now let's prove the theorem. Since it's an if and only if theorem, we need to show both directions are correct. Let's first show the only if part, which is given that a statistic is sufficient, we can factorize it into g and h. So suppose that t of x is a sufficient statistics. This is our assumption when we are proving the only if part. We can write the joint distribution of fx. Let's write down the PDF of fx. By definition, it's the probability of x equal to x using the parameter theta. Here we want to introduce t of x into this probability. If we apply this t of x onto our x space, then we will have t of x equal to t of x, and x equal to x given theta. Just to remind you guys, the capital X is the random variable itself, and the lowercase x is the realization. We also call it the data. So let's first look at how we can write out this joint probability. So what is the, let's first see how can we write out this conditional probability. By the definition, we can write it as the product of the joint, which is exactly what we were looking for, divided by the marginal of t of x. So if we move this term to the left, we actually get what we want. So the joint probability can be written as the product of conditional probability times the marginal probability, and you will see why we need to rewrite it in this form. Now we successfully factorize fx into two probability. Let's look at this marginal probability first. This is a good candidate for g of tx given theta, because it's a function of tx, but it can also depend on parameter theta. And on the other hand, this is a good candidate for hx. Remember we said hx is constant to theta. Let's pause for a moment and think about why this is a constant function to theta. It's because we assume that t of x is a sufficient statistic. Under this assumption, and by definition, given t of x, the original data itself provides no information about theta. That's why this function should not include theta. So we successfully show that if we have a sufficient statistics, then we can factorize the joint the PDF of x into hx and gtx into hx and gtx. Now let's prove the other way. So we want to show the if part, which is proving from factorization to sufficiency. If we are able to factorize a PDF, then we claim that t of x is a sufficient statistics. So in this case, we started by assuming that the factorization fx equal to gtx times hx exists, and we let qt to be the PMF of t of x, and partition A t to be all the points that satisfy ty equal to t. Then we're able to rewrite this PMF of t of x as the probability that tx equal to t, which is the sum of probability of y when y is within this partition. So let's draw a picture of this. Let's say we have a bunch of y. And we're doing a transformation that's called t of y, which happens to be the statistic. After this transformation, we obtain some t value. Let's say we have m elements in the space T, and we now make a partition in this T space. Let's say T of y1, T of y2, T of y4 is equal to lowercase t1. Then the partition we define here is actually y1, y2, and y4. Similarly, if we look at another t value, if we look at t2, and we figure that t of y3 and t of yn is equal to t2, then y2 and yn are two elements within a t2. Similarly, we can do this for all the different possibility of t of m, and that's how we make partitions. That's what partition AT means. So if we look back, it is a probability that t of x is equal to t1. Because there are three y's that can be transformed into t1, so this can be written as probability that x is equal to y1 plus the probability that x is equal to y2 and the probability x is equal to y4, which can be written as the sum that when y belongs to this A1 partition, the PDF of each y. Similarly, if we're looking at what will be the probability that Tx is equal to T2, and this is the orange region right here, so we can write it as the probability that x is equal to y2 plus the probability that x is equal to yn, since we know there are only two elements in this A2 partition. So we can write it as the sum of PDF of y when y belongs to this A2. So if we generalize this idea to P probability that T of x is equal to a T, and this T here is a generic T, then the probability of that can be written as the sum of fx, y, theta when y is belong to this AT partition. Our goal is to show that T of x is a sufficient statistics. And remember, we already knew that there are two ways we can show that T of x is sufficient. We can either use the definition, or we can use the theorem where we take the ratio of the PDF of x and the marginal PDF of the statistic. So let's do that here. Let's see if this ratio is indeed a constant of theta. If we can show this ratio is a constant of theta, then we show that T of x is a sufficient statistic. So by our assumption, we know we can rewrite this PDF into the factorization form. The next thing we do is we use this identity here we just showed to rewrite the PDF of Tx. So we can write it as the sum that A belongs to A of Tx of Fx, summing up all the y. Let's use our assumption again. Because let's do the factorization again. So let's factorize this to be g of t of y times hy, just like what we did here. Okay, so let's move that here. Let's take a closer look at this term right here. Because we know y belongs to the partition of t of x, which is the same way as saying t of y is equal to t of x. So for each y, you always have gt of y equal to gt of x. That's why we can rewrite this part as g of t of x given theta times the sum of h of y. This is simply because this term, as we show here, is equal to a function of t of x, which will be the same no matter which partition you're looking at. So that's why we can move it outside of this summation sign. We have the same term in the numerator and the denominator, so we can cancel it out. What we left here is h of x and the sum of hy, which by the factorization assumption does not depend on theta. So the whole thing is a constant function of theta. So we show that if we assume the factorization exists, then t of x is a sufficient statistics. By showing both the only if part and the if part, we complete the proof for the factorization theorem. Okay. To sum up, t of x is a sufficient statistic for theta if and only if there exists g and h such that the PDF of x can be written as a function of t of x and a function of hx, which does not involve any theta. Let's look at one example. hxi follows a Bernoulli distribution with a parameter p. And let's see how we factorize this joint probability here. We know their IID, so we can write it as the probability that x1 is equal to x1 times the probability that x2 is equal to x2 So let's see how we can factorize this joint probability. This is equal to the probability that x1 is equal to x1, probability x2 is equal to x2, all the way to probability of xn is equal to xn. Since they are IDKs, this equality holds. And let's plug in the PDF. Now, we can combine the p terms, which is the same as p to the power of sum of xi, and let's combine the 1 minus p terms. In total, there are n 1 minus p terms. That's why we're going to have n1 minus the sum of xi. And we know that t of x we're interested in is the sum of xi. So we can substitute the sum of xi by t of x. Let's re-examine this factorization. Let's look at this factorization right here. Apparently, if we call this whole thing a function of t of x, then we found our g, and we can define a trivial hx as hx equal to 1. So, by the theorem of factorization, by the factorization theorem, we successfully show that the joint distribution of fx can be factorized into a function of tx and a function of x, and that's why we can claim that t of x is a sufficient statistic for p. Let's look at another example. Let's look at a uniform sufficient statistic. So x1, xn are IID observation uniformly draw from 1 to theta. And their PDF has the following form. If x belongs to the range, belongs to the domain of uniform, then the PDF is going to be 1 over theta. If x is out of the range from 1 to theta, then the PDF of x is going to be 0. And we are going to find a sufficient statistic for theta using the factorization theorem. Again, let's write out the joint distribution. Because they're ID, so it's the same as writing probability that x1 equal to x1 times probability that x2 equals to x2 all the way to probability xn equal to xn. And we know that the probability that x1 equal to x1 will be theta 1 if x1 belongs to if x1 is within this range. So this indicator function is equal to 1 if x1 is between 1 and theta, and it's going to be 0 if x1 is not belong to 1 to theta. That's what it means of an indicator function. And similarly, we are going to use another indicator function for x2. And then we're going to extend this. We'll also have one indicator function for xn. And let's combine the theta 1 over theta terms. We have n 1 over theta, so it's equal to 1 over theta to the power of n, And for the rest of the indicators, indicator function has one important property. So I of A1 and A2 and AN is equal to I of A1 times I of A2 times I of AN. Because of this equality, we can essentially rewrite the product of n i's into one product, which is x1, x2, and xn is belong to one theta. What does this mean here? It means that we want all the x to fall in the range of 1 and theta. So the minimum of x should be greater than or equal to 1 and should less than the maximum of theta, which is less than theta. Let's break the identity into two parts. The first part is that x mean is greater than 1 and x max is less than or equal to theta. The reason that I break down this into two parts is because apparently the first part has no theta in it and the second part has theta in it. So let's rewrite this identity. I x max is less than or equal to theta times I that x minimum is greater than or equal to 1. This is the g t of x given theta. And this is our hx, which has nothing to do with theta. We have successfully shown that the distribution, the PDF of x can be factorized into g of x and hx. And we can define our t of x to be the order statistic x max. The last example I want to show is the normal distribution example. Imagining you have x1 to xn, their IID follows normal of mean mu and variance sigma square. Assuming both mu and sigma square are unknown parameters. So in this case, the parameter of interest is indeed a vector with mu and sigma square. And let's use factorization theorem to find a sufficient statistics for theta. Let's first decompose this joint probability. Because the random variables are independent of each other, so we can write the joint distribution into the product form. And we know that each marginal looks like this. Has no I in it, we can move it out of the product sign. So this will be 2 pi sigma square to the power of negative n minus 2. Then we're doing another calculation tricks. Imagining you're doing EYI times EY2 times EY3, just like what we have here, the product of a bunch of exponential terms. It's the same as EY1 plus Y2 plus Y3. So here we can write it as EXP of sum from starting from I equal to 1 to n of negative xi minus mu square divided by 2 sigma square. Within the summation, each term has the all the terms have negative sign, so we can move this negative sign out of the summation term. At the same time, let's do some changes to this quadratic term right here. This is a common trick we use all the time. We minus x bar first, then we add it back, and we have minus mu left. Since this 2 sigma square is also a constant, we can move it outside the summation term, the summation sign. And let's expand this quadratic term. A plus b squared equal to a squared plus b squared plus 2ab. So xi minus x bar squared plus x bar minus mu squared plus the middle term 2xi minus x bar times x bar minus mu. Closer look at this summation term right here. This is equal to the sum from 1 to n xi minus x bar squared plus the sum from 1 to n x bar minus mu squared plus 2 times the sum from 1 to n xi minus x bar times x bar minus mu. The first thing you should notice is that this term has no I involved, so you're essentially, so this is equivalent to n times x bar minus mu squared. And let's look at this term right here. Again, because this is a constant, x minus mu is a constant, we can move it outside. And what we left here is the sum of xi minus x bar. If you expand this term, it's actually I from 1 to n xi minus n times x bar. And n times x bar is exactly equal to n times sum of xi divided by n, and we cancel out the n. We're left with sum of xi minus sum of xi, which means this term is 0. Since this term is 0, the middle term can be removed. So this term is 0 right here. Within the parentheses, we only have 2 terms left. So let's put everything together. So we have this cross product term to be 0. What are we left with? We're left with all the constant times the sum from I to n xi minus x bar squared minus, because this term has nothing to do with n, so if we are adding it for n, we were adding n of the quadratic term together, we will end up getting n times x bar minus mu squared. Let's remind ourselves, theta is actually equal to mu and sigma square. So we have a theta, part of the theta here, and here, and here, right? If we propose a t of x with 2 dimensions, x to be x bar, and t2 of x to be the other term right here, xi minus x bar squared. And then this whole thing here is a function of both t1 of x and t2 of x. And what will be our hx? We cannot further factorize this into a function only with x, since every term here involves both theta and x. So the only hx we can come up with is this trivial case. So we successfully write the PDF of x into two functions. One is this g t1x, t2x, and the other function is this hx. Thus, by applying the theorem, we show that tx equal to t1x, t2x is a sufficient statistics for theta. To summarize in this video, we first provided a proof for the factorization theorem. Then we apply factorization theorem to three different problems. One is Bernoulli distribution, one is uniform distribution, and the last one is the normal distribution.